Okay, so I think we're recording now. Good evening again, everybody. I hope you're having a good night despite I think the heavy rainfall, at least from where am I at. So medyo malakas yung ulan maghapon, though it's quite a nice a breather from a couple of weeks that are characterized by intense heat. But I hope you are dry and safe wherever you are, kung maulan dyan or not. But we are here again to talk about some linear algebra. Again, I wasn't able to meet you live last Wednesday due to a prior engagement, but I hope you watched the video that I asked you to watch, which is basically the recording way back in 2021. So don't pay attention too much on the deadlines or the dates mentioned there. That will be off definitely. But what I wanted you to take away from that video would be the discussion of the remaining parts of module number 2 that we didn't finish, and then certain parts of module number 3, essentially the definition of what a linear transformation is, so that we can move on and take a look at some more meaty parts of the course. But unfortunately, I don't think we can finish everything that we covered last or 2 semesters back. But whatever the case would be, I will be providing you a copy of all the modules we used. Pero definitely the coverage of all our assessments, plus if you'll be taking the comprehensive exam under me in the next terms, uh, it will be uh, it will be limited to whatever we finish discussing in class. Ano, hindi nakasama yung parts ng module na hindi natin mapapag-usapan in class. And then just a quick update. Medyo nagkamali pala ako. I thought I finished grading homework number 1 last time. At least those who submitted early when I mean early when I started checking it. Tatatlo pa lang pala yung na-checkan ko. I thought I finished checking all 4 of your submissions, but I think I finished grading 2.1 what was that? I think I graded the fourth the fourth problem then, and then I finished grading 2.2 the other day, and then 2.1 kani-kanina lang. So all your scores should be divided by 40. So yun yung makikita yung standing right now. If you're still missing some of the works, pero hindi nyo pa na-submit lahat ng mga yon, or hindi ko pa na-checkan, naka-over 40 na yung standing. So the standing that you are seeing is over 40. So meaning I assume that I graded all of your works. If there are still some pending works that I haven't graded, so tataas pa yung standing nyo definitely. So kayo mag-alala, kung may isa pa akong di na-checkan sa inyo, so assume 0 kayo dun sa nakikita nyo standing. Once I grade that missing, remaining homework of yours, tataas definitely yung standing. Medyo quirky lang si Moodle kasi ang hirap kontrolin ng formulas, kaya ganon. So, and then I'll try to finish grading the third problem in homework number 2 tonight and see how will I get para by early next week you'll get the feel of how you are doing in the course. So now let's move on, but let's take a quick look at the parts of the module that were covered, or the modules that were covered in the recording you watched last Wednesday. And then as I go along these results, you can raise your hand or you can intervene. You can interject anytime to let me know if you have some questions about these results. I'll just be going over them quickly para lang ma-review tayo, especially those results that we'll be needing in our discussion today, right? Now, I don't know exactly if we discussed Proposition 10 live last Saturday, or was it part of the recording you watched. But Proposition 10, siguro bago pala Proposition 10, ano, balikan natin yung konsepto ng basis. So a basis is basically a subset of a vector space, right? And it has 2 properties. The vectors inside the basis are linearly independent, meaning not one of them can be written as a linear combination of the others. And then number 2, the span, or the generated set of the basis is equal to the entire vector space V. So you can think of the basis elements as representatives of the vector space that can in which you can expand, or with respect to whom you can expand other elements of the vector space. So we said, kasi generate ng basis yung buong vector space, so kahit na anong vector v dun sa vector space ay kaya nating masulat as a linear combination of the basis elements b1, b2 until bn. All right, and then the b sub i's, the basis elements are linearly independent. Right. So that's one way. That's one interesting way. So every vector in V can be written as a linear combination of the elements of B, the basis, and you can do so only in a unique way. That's what proposition 10 is telling us. So pag may napili ka ng isang basis para sa yung vector space, isa lang nag-iisa lang, unique lang yung linear combination na magre-represent sa isang vector kay V as a linear combination ng mga basis elements. So, yun yung kagandahan ng basis kasi hindi isa lang yung expansion dun sa nung isang vector in terms of the basis, in terms of the basis elements. So, hindi ka makakita ng dalawang magkaibang basis expansions para sa para sa isang vector. So, that will be unique. So that's what proposition 10 is telling us. So that simplifies our work in most of the proofs. You don't need to select a particular basis expansion because anyway, there's one and only one such basis expansion. So kaya madali yung mga proofs na ginagawa natin. Okay. Now, proposition 11 just tells us na ang isang linearly independent set ay napapaloob sa isang basis. This is a consequence of a basis being the maximal linearly independent set. So we expect that all linearly independent subsets of a vector space will be properly contained in some basis for V. All right. And then corollary 12, which is very important, lahat ng vector space ay may basis, which again is building up to our end goal because again, the goal of this course is to study linear transformations and or linear transformations between vector spaces. Now, in order to do so, one could study all the actions of the linear transformation on all the basis elements. Titingnan natin paano nag-act ang isang linear transformation sa lahat ng mga vectors dun sa vector spaces. But we have seen vector spaces can contain infinitely many elements. So it would be impossible to analyze what happens to a vector, to all the vectors under a linear transformation. So we want to limit our study. Now, our candidate ay pag-aralan yung mga basis elements kasi alam natin ang ganda ng property ng basis. Yung basis ay naglalaman ng linearly independent sets at lahat ng vectors ay kayang masulat in terms of the basis elements. Now, nakalimutan nating itanong, lahat ba ng vector spaces ay may basis? The answer is yes, corollary 12. So really, maganda yung pinapatunguhan ng ating discussion because it seems that we can really focus our study on basis rather than on the entire vector space, right? Although what's left to be seen is ano ba yung pag-aaralan natin? Hindi pa natin na-define yung linear transformation, although you have watched it in the video, but formally I'll flash the definition later on. So that's corollary 12. Lahat ng vector spaces ay may basis. Okay? Kaya lang hindi natin kayang makonstruct lahat ng mga bases sa katulad ng example na to. Example 29 gives us a vector space na wala pang nakakahanap or nakakapaglista ng basis elements. Alam lang natin na may nag-exist na basis para sa kanila by corollary 12, but nobody have constructed explicitly how that basis looks like. So that's the wonderful thing about math. We can say that something exists without even knowing how it looks like, right? So parang yung corollary number 12. Lemma 13 is just a technical result, which tells us that kapag ka meron kang linearly independent set, yung cardinality niya ay hindi lalampas sa cardinality ng basis. Again, a consequence of the maximality of the basis. And then lemma 13 is just a prelude to theorem 14, the dimension theorem for vector spaces. And this is an important result, and I really love to ask it during comprehensive exams. I ask students to either state the dimension theorem or the dimension invariance theorem for vector spaces, or say something about its significance. Ano? So usually I call it the dimension. Pwede nating lagyan ng invariance para mas madali nating matandaan. So the dimension invariance theorem tells us na, again, alam natin na lahat ng vector spaces ay may basis. Alright, that's fine. Tapos nakakita tayo ng mga examples na ang basis ay hindi unique. Pwede kang magkaroon ng iba't ibang basis para sa isang vector space. Now, Theorem 14 gives us the relationship between different bases for a vector space. It tells us na magkakasing dami lamang ang laman ng isang basis para sa isang vector space. So if you have two different bases for a vector space, then we are guaranteed that they will have the same cardinality. All right. Theorem 14 guarantees that for finitely generated vector spaces, pag finite yung dimension ng basis, as not dimension, it's a technical term, but kapag kapag finite yung dami ng basis elements sa isang vector space, then kahit ano pang ibang basis, ganun din kadami yung magiging laman niya. So really, we have mentioned that gagamitin natin yung ang isang basis para pag-aralan ang action ng linear transformation sa isang vector space. Now, maraming bases para sa isang vector space. So intuitively, we want to pick which basis has the least number of elements. But Theorem 14 discourages us from doing that because that will be nonsense kasi sabi ng Theorem 14, magkakasing dami lamang ang laman ng kahit na anong dalawang magkaibang bases para sa same vector space, right? I don't usually ask students to prove the dimension invariance theorem, but we have shown the proof here. So if you want to take a look at it. And then the general dimension invariance theorem is theorem 15 na sinasabi na magkakasing dami sila kahit infinitely many yung laman nung basis. So sinasabi niya, we can pair in a one-to-one correspondence or via a bijection yung elements para sa dalawang bases. So essentially, pinapalaki lang ng Theorem 15 yung Theorem 14. Sabi ng Theorem 14, kapag finite yung dimension, yung cardinality o yung dami ng laman ng isang basis, then ganun din kadami yung laman nung iba pang bases. So ibig sabihin, kung finite yung number, equal lang, magkasing dami lang sila. Theorem 15 in layman's terms tells us na ganun din kapag ka infinitely many yung laman ng isang basis. So kung infinite yung laman ng isang basis, then lahat ng iba pang bases ay infinitely many rin yung laman. Though Theorem 15 is more technical kasi for mathematicians, meron pang iba't ibang levels ng infinity. So merong level 1, which is Aleph 0, yung kasing dami ng natural numbers. Tapos may Aleph 1, kasing dami naman ng real numbers. So hindi magkakasing dami or magkakasing dami yung laman ng mga infinities. So kaya sinasabi ng Theorem 15, essentially, kapag anong klaseng infinity yung nasa isang basis, ganun din yung klase ng infinity na nandun sa kabilang basis. Kung finite, walang problema. Equal lang yung number of elements nila. Kaya lang pagka infinitely many na yung laman ng isang basis, meron yung isang klase ng infinity, ganun din klase ng infinity yung laman ng iba pang mga bases. Right? Just some technical details there. That's why I did say this is they have the same number. Kasi pwede mo sabihin infinity and infinity are the same, but no, not all infinities are created equal. Some infinities are greater than others. So basically, that's the essence of Theorem 15. Then there are this is followed by several more examples. I hope you went through them. Then Proposition 16 is basically a technical result involving basis. Oh, but before that, I think dinefine muna yung dimension. All right? Kasi ngayon, alam na natin na lahat ng paulit-ulit ako, pero it's nice to repeat things. It will aid in remembering. Lahat ng vector spaces ay may basis. Posibleng maraming basis para sa isang vector space, ngunit magkakasing dami lamang lahat ng mga basis, ang mga laman ng mga bases. So ibig sabihin, we can call that special number the cardinality of any one of the bases by a nice name. So it could be a characteristic of the vector space itself. And with that, we will call that number, the cardinality of any one of the bases, to be the dimension of the vector space. And we usually write it as dim of V. And this is well defined kasi sabi natin, ang dimension, dinidefine dito, ang dimension ng isang vector space ay ang dami ng laman ng basis sorry. Ito, ang dami ng laman ng isang basis. Bibilangin mo ilan yung laman ng isang basis. It is well defined kasi magkakasing dami lang naman yung laman ng mga bases. So ibig sabihin, isa lang yung number. Kahit ano pang base yung piliin mo, isa lang yung makukuha mong cardinality. And we call that cardinality the dimension. Kung magkakaiba yung dami ng bases, we cannot define what a dimension is. Kasi posible magkakaiba tayo ng makompute na dimension. Pero thanks to the dimension invariance theorem, magkakasing dami lang pala yan. So pipili lang ako ng madaling basis, for instance, the elementary or the canonical basis, malalaman ko na yung dimension ng isang vector space. Right? So here are some examples of computing the basis. All right. So let's see, what's the other important thing here? I'm almost at the end. So that ends module 2. But before we go to module 3, yes, Sol, may tanong ka?
Sir, good evening po.
Good evening.
So, wala pong cardinality ang vector space. Dimension yung tawag natin sa ano niya, sa parang number niya, ganun po.
May cardinality ang vector space, though hindi natin siya concerned. Basically, when we say cardinality, yan lang yung dami ng elements niya, no? So, wala tayong pakialam sa dami ng laman ng vector space. Ang tinatawag nating dimension ay yung dami ng laman ng isang basis niya.
Okay. So, incorrect po kapag incorrect po yung equal yung cardinality ng vector space sa kanyang dimension.
Yes po. Ang cardinality ng basis ay hindi equal sa kanyang dimension. Kasi
Thank you, sir.
You're welcome, Sol. Kasi ang dimension ng vector space ay cardinality ng basis. Gaano kadami yung basis niya. So as an example, I think we have here what? Sige, tingnan natin isang example. It's nice that you're picking up on those technical details, ano, na ngayon medyo medyo careful tayo sa mga sinasabi nating equalities. Diba si R3? So ang R3 ay set of all three vectors. So siya ay tatlong real numbers lang, right? So this is ang mga laman ni R3 halimbawa ay 1, 0, 0, 0, 1, 0, at saka 0, 0, 1. Alright? Actually, ito ay mga example ng mga vectors kay R3. And incidentally, this is, or they comprise the canonical basis or the elementary basis for R3. Kasi lahat ng elements ni R3 ay kaya nating masulat as a combination, as a linear combination of 1, 0, 0, 0, 1, 0, and 0, 0, 1. Tapos linearly independent yung tatlo na yan. So in fact, this is a basis. So meron siyang tatlong laman. So masasabi natin ang dimension ni R3 ay 3. Actually, in general, ang dimension ni Rn ay n. Right? Pero ang cardinality ng R3 ay Aleph what? It's Aleph, I think it's Aleph 1. It's Aleph 1. So, ibig sabihin, magkasing dami ang real numbers at saka yung laman ni R3. Let me think about that. Yeah, I think that's correct. So, ganyan kadami siya. So, infinitely many yung laman ni R3, pero 3 lang yung kanyang dimension. Kasi ang binibilang natin sa dimension ay yung kanyang number of basis elements. Right? And I think this is also the reason why, for instance, sa geometry, pagka tayo ay nag-graph ng mga vectors in R3, tatlo lamang yung coordinates na ginagawa natin. So meron kang x-coordinate, y-coordinate, at z-coordinate pag nag-graph ka kay R3. Kasi yung vector 1, 0, 0, printed pala yung aking anyway, you can orient it any way you like. So usually itong x, ito yung y, at saka ito yung z, right? Ito yung vector 0, 1, 0, 0. Ito yung vector 0, 1, 0. Tapos ito yung vector 0, 0, 1, right? I don't know if you have wondered, bakit kaya nating i-graph lahat ng elements ni R3 using 3 coordinate axis? And the reason there is kasi lahat ng vectors sa R3 ay kaya kong masulat as a linear combination of the 3 unit vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1, 0. Kaya pag meron kang 1, 1, 3 na vector, 1, 1, 3, kailangan mo lang hanapin yung 1 dito, kailangan mo lang hanapin yung 3 dito, tas yung 1 dito sa y, tas yung 3 sa z. Kasi pwede mo siyang isulat as 1 times 100 plus 1 times 010 plus 3 times 001. Kaya maplaplot mo siya somewhere here. Ito yung vector 113. And we can do that kasi nga ang basis ni R3 ay tatlo lamang yung laman. So, sufficient na magawa ka ng tatlong coordinate axis, pipili ka ng basis, tas bawat isang basis element magkakaroon ng isang corresponding axis, tas lahat masusulat mo using the coordinates na i-define ko later. Pero kaya ganun din yung dimension ng n-dimensional spaces. Halimbawa sa 3D, kaya siya 3-dimensional kasi ang domain ng vectors in that space sa 3-dimensional space ay tatlo yung laman. So kailangan mo lang ng tatlong coordinate axis. So some intersections between different branches of math. But anyway, that's the portion of module number 2 that we were not able to tackle last time. So or live at least, you watched that in the video. Then let's see the first part of module number 3 that was tackled in the second video that I asked you to watch. Nalata ba nagmamadali na ako kasi kailangan kong maano sa inyo, makaabot tayo at least sa module 4, and then 5 and 6 could be supplementary materials. Okay, now I kept on blabbering about linear transformations because that's really what's the intention of linear algebra. Kaya nga may linear sa title, linear transformations. So kailangan natin yung linear transformations at yung structure niya. Kaya may algebra dun sa pangalan. Now, in here, in module number 3, by the way, you'll need to answer how many? 5 problems. Hindi ko na siya binawasan kasi I decided that the grading scheme now would be sum of your scores in the homework divided by the total perfect score. When I say total perfect score, yung walang premium, ano? So, kung over 5 lang yon, then if you get a perfect score with a premium, so you're gonna get 5.5 over 5. So yun yun. Pero sa Moodle nga pala, naka-tag na 6 points yung maximum. Kasi nga ayaw akong payagan ni Moodle na magbigay ng 5.5 over 5. So kaya kailangan kong ng turnaround, ng workaround from that quirkiness of Moodle. But anyway, so the target date is July 21st. So let me know if you're gonna need more time. But I guess that would be enough. Pag hindi, extend natin. Sabihan nyo ako probably middle of next week if you need more time to finish it with the premium. Pero if you can finish it early, then that's great. Okay. Now, tingnan natin yung mga parts ng modules na to na kailangan natin for today. Of course, we'll need definition 7. Definition 7 finally defines what a linear transformation is. Ang isang linear transformation na isa lamang function between two vector spaces that has nice properties. All right? So, dapat si L, siya yung pangalan natin sa linear transformation. Ito ay isang function na nagdadala mula sa isang vector kay V papunta sa isang vector kay W. So, V and W here are vector spaces over the same field. Over the same field nga ba? No, they could be coming from different fields. But in this definition, I just assume there's a single field involved. But in general, there could be... hold on. No, no, no. Tama pala yung definition. Dapat ay parehas yung field, yung underlying field dun sa dalawang vector spaces. Because I need that in in definition 7.2. So essentially, meron kang dalawang vector spaces, V and then W, na may same underlying field F. Tapos, si L ay isang function mula kay V papunta kay W, tinatransform ni L yung mga vectors kay V papunta sa vectors in W. So pag binigyan kita ng vector V, of course, this will be coming from the set V or the vector space V. Ita-transform siya ni L kay W, which would be L of V. Yung function value ni V under L ay equal kay W na isang vector naman kay W. Alright? Kaya siya tinatawag na transformation. Tinatransform niya yung isang vector kay V papunta sa isang vector kay W. Now, hindi lang siya basta-basta transformation. It's a linear transformation. Now, to be called a linear transformation, kailangan na pre-preserve mo yung linearity nung vector space. When we say linearity, dalawang bagay yung kailangan yung i-check. Una, yung function value ng sum ng vectors ay sum ng function value ng vectors. So L of V1 plus V2 dapat equal yan pag sa L of V1 plus L of V2. So essentially, this tells us that the vector addition in the two vector spaces are preserved. Kasi it doesn't matter if you take the sum of the vectors v1 and v2 first, then plugging it into L, or plugging v1 and v2 first respectively to L, and then take the sum. Parehas lang yung number mong makukuha. So essentially, itong property number 1, pinipreserve niya yung addition. Kasi yung addition kay V ay natatransform sa addition kay W. Kasi remember, L of V1, ito ay manggagaling kay W. L of V2 ay manggagaling din kay W. So essentially, parang ang laki ng binibigay nating relationship sa addition kay V. Dalawang mag-iibang addition nga pala to, but I'm doing abuse of notation just to avoid too much different symbols. Pero yung addition dito sa kaliwa, ito ay addition kay V. Tapos itong sa kanan, ang addition dito ay kay W. It's clear in context kasi ito ay nanggagaling kay W, ito ay nanggagaling kay W, so marapat lamang nang gamitin kong addition dito ay yung addition kay W. Samantalang dito naman, si V1 at si V2 ay mga vectors galing kay V, so dapat ang gamitin kong addition sa kanila yung addition sa unang vector space. So essentially, addition should be preserved. The image of a sum should be the sum of the images. Sum of images. The second property that you need to check is the preservation of scalar multiplication. So it shouldn't matter kung gagawin mo muna yung scalar multiplication, saka mo ipa-plug in kay L, or ipa-plug in mo muna yung vector kay L bago mo siya i-multiply ng scalar. So essentially, we are also preserving scalar multiplication. All right? So pag pinagpo-prove ko kayo kung na linear transformation ng isang function, kailangan yung i-check condition 1 and condition 2. All right? And a linear transformation is also called a homomorphism. Naabot niyo na ba ito sa abstract algebra? I know you will be encountering homomorphisms as well in linear algebra. Nakapag-group homomorphism na ba kayo or hindi pa?
Magkasabay po, sir, ngayong ngayong week.
Ngayong week. Okay, good. So, sana hindi siya mag-create ng confusion, ano? Pero sa group homomorphism, ang pinipreserve niya ay yung operations sa groups. Pagka nagkaroon na kayo ng ganun din naman sa rings, pero kakaiba tong homomorphism sa linear transformation. Kasi ang i-preserve natin dapat ay addition sa scalar multiplication. Sa group walang problema. Sa group homomorphism nyo sa abstract, kasi isa lang naman yung operation na ginagalawan nyo. So isa lang yung operation, isa lang yung dapat ma-preserve. Pag ring homomorphism, dalawa na yung operation, so yung dalawang operations na yon yung ma-preserve. Pero pag homomorphism sa linear algebra, meron tayong dalawang operation between vector spaces. Yung dalawang operations na yon yung dapat ma-preserve. Right? I think, go Sol.
Oo. So na-confuse na nga ako, sir. So yung addition dito sa kaliwa, pwede siyang, for example, kasi sa V siya, modulo 2, for example. Tapos pagdating niya sa kanan, modulo 4 na siya, for example.
Yes.
Okay.
So kasi you're right, because isang example, halimbawa si L ay isang transformation mula kay Z2 hanggang kay Z4. So, etong mga to na kay Z2, so addition mod 2 yung gagamitin nyo. Dito naman, dahil si LV1 saka si LV2 ay galing kay Z4, so addition modulo 4. Though mahilig ang mga mathematicians na sabihin na dapat consistent tayo at very particular in what we're saying, but we're also fans of abuse of notation. All right? Magkaiba itong dalawang addition na to. But we always say that should be clear in context because you cannot add, halimbawa, you cannot add modulo 2, mga elements ni Z4. So that wouldn't make any sense. So yeah, whenever there are confusions there, just let me know. Ano? Pero usually in context, pag magko-compute na kayo, marirealize nyo kung anong addition dapat yung kailangan gamitin. But if it gets confusing, lalo na halimbawa sa exercises or sa homeworks, pag hindi siya klaro, gagamit ako ng dalawang magkaibang symbols para sa dalawang addition na to. Okay. Right. So yeah, so that's it. Now, remark number 3 is also a good thing. Ano? So, pag meron kang homomorphism o isang linear transformation, dapat ang image lagi ng zero vector ay equal sa zero vector naman nung kabilang vector space. That's always required. Kapag ka linear transformation ka, pinasok mo yung additive identity ng vector V, ang lalabas under the transformation dapat lagi ay additive identity ng vector W. All right? So that should always be the case. And then I hope you can write a proof for it. Ang clue para sa proof niya ay kunin niyo yung, di ba meron kang L of OV? Sorry. Meron kang L of 0. L of 0V. Gusto nating ipakita na ito ay equal sa 0 kay W, right? Sulat mo to as L of V minus V. Right? Si 0 vector kay V, isulat mo as V minus V. And then you apply linearity ni L para mapakita eventually na ito ay equal kay 0 vector kay W. 0 vector kay W. Right? So yan yung trick para sa proof nito. Maganda pala itong pa-compare exam. So take note of that. Baka maalala ko siya pag susulat ko na yung exam nyo, pwede ko siyang isama. Remark 3 is a good exercise for proving. Pero yun yung trick. Okay. So then, couple of examples here. Yeah. Mga klase ng example ng transformations. And then here you will see what else? Yeah, you will see different examples of linear transformations and how to prove that a certain function is a linear transformation. But essentially, two bullets yon. L of V1 plus V2 ay equals to L of V1 plus L of V2, and L of alpha V ay equals to alpha of LV. So yun yung kailangan yung gawin para ma-prove na siya isang linear transformation. Theorem 17, this talks about graphs. Ano? This is not too important in our context, but it's not a nice example nevertheless. So ito naman ay yung linear transformation, how you transform a certain graph to another, right? But it's a good example, pero I don't think we will use that tonight too much. So I'll skip on that, but kindly go back to it in the recording if you want. Okay, so ganon yung linear transformations o homomorphisms. Now, in algebra, we always want to look at the structure of our objects. Now, pag kinolekta natin lahat ng posibleng linear transformations from a vector V to a vector W, then we're gonna get a nice set, a nice property. And it's too nice that we gave it a name. Ang pangalan niya ay hom of VW. So ang hom of V, W, ito lamang ay ang set ng lahat ng linear transformations from vector V to vector W. So kukolektahin lang natin lahat ng posibleng linear transformations from vector V to vector W, and then we look at its properties or its characteristics as a set. And it turns out that the set of all homomorphisms or the set of all linear transformations constitute a vector space under the usual addition and scalar multiplication. So remember, I think sa homework 2.1, pinrove nyo ng set of all functions from x to y, from a set x to a set y is a vector space, right? So equivalently, pag pinalitan ko si x at saka si y ng vector spaces, the set of all functions from vector space V to vector space W ay isang vector space. Now, proposition 18 is telling us that the set of all linear transformations ay subspace. Sorry. Proposition 18 is telling us that the set of all homomorphisms from V to W is a vector space. Pero dahil lahat ng homomorphisms ay functions in the first place, so lahat ng linear transformations ay nandito sa set of all functions. So basically, hom of VW is a subset of f of VW. So that's why I think the proof of proposition 18 took advantage of that observation and proved that the set of all linear transformations is a vector space by using the compact criterion for subspaces. Pinakita niya na si hom VW ay subspace ng f of VW. Kasi mas madali yung ipakita. Hindi niya na kailangan dumaan dun sa ginawa niya sa homework 2.1 na i-check yung ilan ba yun, siyam na properties para makonclude na si hom VW ay isang vector space. Pinakita niya lamang yung compact criterion, yung closure under vector addition and scalar multiplication para mapakita na si hom VW ay subspace ni F at dahil subspace siya, vector space siya in its own right. And that's a nice property that we want with the homomorphisms kasi nga meron din siyang vector space property. Okay? So here's the proof. And I guess the recording stopped at theorem 19 kung di ako nagkakamali. Okay. Theorem 19 tells lays down the groundwork for yung gusto nating mangyari. Palapit na tayong palapit dun sa gustong mangyari. Again, gusto nating pag-aralan ang action ng mga linear transformations sa vector spaces. Ano yung ginagawa ng mga linear transformation sa mga vector spaces? Now, how do we study that? Of course, the brute force is to study the effect of linear transformations on all vectors. But that's quite a heavy task. So that's why we want to study at a certain class of vectors na kayang mag-represent sa lahat ng mga vectors dun sa vector space. And that turns out to be the elements of a basis for a vector space. So essentially, our linear algebra goal boils down to studying the effects of linear transformations to basis elements. Kasi nga maganda yung kakunti ang laman ng basis at yung basis nire-represent niya yung buong vector space. So pag-aaralan natin anong ginagawa ng mga linear transformations sa mga bases. Right? Tapos yung knowledge na makukuha natin from that study will give us ideas kung paano nagwo-work yung linear transformation doon sa buong vector space. And theorem 19 starts that. So ano ba ang sinasabi ng theorem 19? Let's pick it phrase by phrase. So kukuha tayo ng dalawang vector spaces V and W. Tapos pipili na ako ng isang basis para kay V. Ang basis ko para kay V ay si B, si curly B. Now, kung si F ay isang function na nag-work sa basis elements, so essentially, ang domain ni little f ay yung basis vectors, right? So pag meron kang basis vectors, pwede natin siyang i-plug in kay f, tapos yung makukuha nating f of b, siya ay na kay w. So si f ay isang function, si little f ay isang function na nagdadala sa isang basis vector papunta sa vector space W. It transforms a basis element to a vector in W. Now, sa bawat isang function f daw, makakakuha tayo ng isang homomorphism na si L, na ang function value ng vector space ng basis element under L ay equals to f of b. Right? Remember, si f ay nag-act sa basis b. So lahat ng basis elements, lahat ng mga vectors na naka curly B ay merong f of B. Meron siyang function value under B. Now, kung gusto mo raw gumawa ng isang homomorphism, pumili ka lang ng isang function na mag-a-act sa basis elements at ang Theorem 19 ang mag-guarantee sa atin na may makikita tayong unique na homomorphism in such a way na ang function value ng basis elements ni V ay equal sa f of B. And then, of course, capital L, iba na yung domain niya. Ang domain niya na ay si entire vector space V. So parang ang ginagawa ni L, ine-extend niya si F. Kasi si F, ang domain niya lang ay si basis. So mga pwede nyo lang i-plug in kay F ay mga vector basis. Basis vectors. Like that. Ang pwede nyo lang i-plug in kay little f ay mga basis vectors. Pero, pwede raw nating i-extend si f in such a way na ang function value ni B kay L ay f of B rin. Pero ngayon, lahat na ng vectors kay V ay magkakaroon ng function value kay L. So, pwede na kayong mag-plug in ng L of V. Hindi nyo pwedeng gawin yung f of V kasi hindi defined si f sa lahat ng vectors. Si f ay defined lamang para sa basis elements. Now, pwede mong extend siya na lahat na ng elements ni V ay magkakaroon ng image under L, and the nice thing about that, you can select L to be a homomorphism. So ganito pa lang isang paraan para mag-create ng isang homomorphism, ng isang linear transformation. Kasi before Theorem 19, what we're doing is defining L first and then checking if it's a linear transformation. What if out of the blue, I ask you to create a linear transformation? Medyo mahirap mag-define ng isang linear transformation. But Theorem 19 is telling us, madali lang yan. Kunin mo lang yung basis, mag-assign ka lang ng function value dun sa basis elements, tawagin mo siyang f, ginagaranti ni Theorem 19 na may mag-exist na linear transformation base dun sa function na define mo para dun sa basis elements. So think of a correspondence on the basis elements, and that will help us construct a linear transformation. Now, Theorem 19 is quiet on how do we create that linear transformation. Sabi niya lang, kaya mo mag-create. Hindi niya sinabi kung paano mag-create. The nice thing about the way the module was written ay sa proof, ang ginamit natin ay isang constructive proof, which is another kind of proving the existence. Ang ginawa ko sa proof ay pinakita ko kung paano gumawa ng isang ng isang homomorphism coming from a function f. Remember here, the function f could be anything. Wala siyang condition. Di siya dapat linear transformation. Wala siyang ibang property. Basta meron kang basis element, imamap niya sa isang vector kay W. Now, pag kaya daw natin siyang extend papunta sa isang linear transformation. Or para sa isang unique na linear transformation. Now, sa proof, sasabihin ko kung paano mo siya ma-extend. And after we go through the proof, you will learn how to create a linear transformation out of thin air. All right, not really out of thin air, but you know the steps. You create, you do a function f, and then from the function little f, you can create the unique linear transformation L. Okay. Now, it's time to go over the proof. So, all right. Remember, nag-start tayo sa basis, sa isang basis B. All right? So, alam na natin ang property ng basis. Pag kumuha ka ng kahit anong vector V din sa vector space, kaya mo siyang masulat in a basis expansion. Right? Ito yung tinatawag natin na basis expansion. Si equation 46. So, kaya kong masulat si V as a linear combination ng mga basis elements. So yung mga B sabay, siya yung mga nanggagaling dun sa ating basis. Tapos yung alpha i's mga scalars galing dun sa field. Now, eto si L. I-define ko kung ano yung L. Ano yung hula ko para dun sa L, dun sa unique L na sinasabi ng theorem na linear transformation at may property na to. Okay? Sabi ko rito, eto yung L na hula ko para dun sa L dun sa theorem. L is a function from V to W, that's fine. such that kahit na nung vector v, kaya kong i-plug in kay L. Right? Pero sabi ko nga kanina, kahit ano pa yung v, kaya ko siyang gawa ng basis expansion. Alright? So ngayon, gagamitin ko yung basis expansion para ma-define ano si L of v. Si L of v ay gagawin kong summation ng alpha I times f of bi. Now, equations 46 and 46.1 looks very similar. Ito ay expansion ni v. Ito yung function value ni v under L. And let's see how was it done. Well, kinopya lang yung summation, so linear combination pa rin siya. Yung scalars para mula dun sa basis expansion, kinopya ko lang doon papunta dun sa L of v. Kaya lang itong b sub I ay pinaltan ko ng f of b sub I. Alright? So, remember, this is coming from v. Yung mga b ay nagagaling kay v kasi nagagaling sila kay b. So, galing siya kay v. So, ang linear combination ng mga elements ni v ay element pa rin ni v. But if you look at here, yung f of bi, ito ay nanggagaling na kay w. I-multiply mo siya ng scalar, so itong buong ito ay element pa rin ni w. Tapos pag kinuha mo yung summation ng mga elements ni w by closure property of w as a vector space, element pa rin siya ni w. So, yung element ni vector space v na transform natin sa isang element ni w. Is that good? So that's why we can say that L is a nice map. And then another thing is, sir, baka naman hindi siya well-defined map. Meaning, pag naiba yung basis expansion ni, posible ba na si V ay masulat ko, ay mabigyan ko ng dalawang function values? Well, that is impossible because unique lamang yung basis representation. I think we mentioned it in the review kanina, ng isang vector ay may unique basis expansion. So, unique lang yung basis expansion. So, unique lang itong makukuha nating summation na to. So, that means the function L is well-defined. So, meron na akong hula para dun sa function L na sinasabi sa theorem. So, kailangan ko ipakita na si L ay isang linear transformation o isa siyang homomorphism at na siya ay unique. Alright? Umpisa ko sa pagpapakita na siya ay isang linear transformation. And again, pagpapakita na siya ay linear transformation, kailangan kong ipakita yung dalawang bagay. Ang L of V1 plus V2 ay equal sa L of V1 plus L of V2 at yung L of lambda V ay equal sa sa alpha of lambda V. Right? Umpisahan ko dun sa preservation ng addition. So, kukuha ko ng dalawang vectors V1 and V2 kay V. Tapos kukunan ko silang dalawa ng basis expansions. So ang basis expansions ni B1, pagpalagay natin ito, summation in terms of the B sub i's. Tapos yung expansion ni V2 ay summation in terms of the B sub I primes. Well, pinag-iba ko lang. Tinawag ko lang itong B sub I at saka itong B sub I prime kasi posibleng magkaiba ng basis elements na kailangan para sa expansion ni V1 at saka ni B2. But per one of the problems in homework 2, I think you can also call it B sub I. Right? Pwedeng pagparehasin nyo sila ng basis elements. So it doesn't matter. I was being extra careful with the expansions, but that's fine. Now, kailangan ko yung expansion ni V1 at saka ni V2 para ma-compute yung L of V1 at saka L of V2 at mapakita na siya ay equal sa L of V1 plus V2. Right? So, ganun yung gagawin ko. So, kukomputing ko yung L of V1 plus L of V2. Now, I think there's a missing part here. I don't know why I missed it. Or ganun ba siya ka-obvious kaya hindi ko na siya sinulat. Well, if you can add, siguro para mas klaro, yung second line dito, dapat kunin ko muna yung L of, papalitan ko muna si V1, sulat ko yung kanyang basis expansion, plus summation ng I going from 1 to N ng beta I B sub I prime. Actually, dapat to ay M. Yeah, that's right. M. Okay? Tapos, ang usapan ngayon ay pag meron ka ng basis expansion, so pwede ko itong isulat na L of alpha 1 B1 plus alpha 2 B2 plus until alpha n Bn. Susulat ko lang na mahaba yung summation plus beta 1 B sub I prime plus beta 2 B sub 1 to, B sub 2 prime plus until beta M B sub M prime. Right? In-expand ko lang yung summation. Tapos, kulang pa rin yung space. Dito ko na lang siya isulat. Ang susunod na line ay ito. Kukunin ko yung function value. Pero ang definition, according dun sa definition ng L na binigay ko sa equation 46.1, ito lang ay equal sa L of, equal lang siya sa alpha 1 f of B1 plus alpha 2 f of B2 plus hanggang alpha n of f of Bn tapos plus beta 1 f of B1 prime plus beta 2 f of B2 prime plus until beta. That should be beta n of f of beta m, b sub m prime, right? Tapos, saka pa lang lalabas ito. So, after you expanded it this way, ibabalik ko siya sa summation notation. If you look at this, guys, the first n terms, ito ay equal lamang dito sa summation ng alpha I f of bi. Tapos, yung n plus first hanggang sa m term, equal lang siya dun sa pangalawang summation. Is that good? Tama ba? Okay, thank you. I think that should be clear. And then this guy is essentially L of V1 by 46.1. And then this is also L of V2 by 46.1. And hence, here we have shown that L of V1 plus V2 equals to L of V1 plus L of V2. So addition was preserved. Okay. Now that's the first half nung pagpapakita na siya isang homomorphism. Yung pangalawang parte nung pagpapakita na siya ay homomorphism ay kunin natin yung L of alpha V. At ang goal natin mapakita na to ay equal kay alpha L of V. All right. But again, I'll just follow equation 46.1, how we define the function L. Well, sabi niya, ito ay L of A, tapos kunin mo lamang yung basis expansion ni V. Pinalitan ko lang si V ng kanyang basis expansion, which is important kasi yung image under L ay nako-compute after mo makita yung basis expansion. Right? But here I will use the distributive property of scalar multiplication over vector addition. I can put the alpha inside of the summation to get this line, right? And then, pwede ko itong i-consider na basis expansion pa rin na yung mga scalars ay alpha alpha I. Tapos ito pa rin yung basis vectors natin. So by equation 46.1, the way we define L, ang L of this guy lang ay kopyahin si summation, kopyahin yung scalars, paltan yung BI ng f of BI. And here we go. Right? Ito yung equals to L of alpha V. But again, our end goal is to show that this guy is equal to this. But that's easy. We can use the distributive property again of scalar multiplication over vector addition so that this alpha can come out of the summation and give us this. But this guy, the one that I will highlight, is exactly L of V by 46.1. And so we have shown that L of alpha V equals to alpha of alpha times LV. So vector addition is preserved. Scalar multiplication is kind of preserved. So we can say that L is indeed a homomorphism. Okay. Any questions with that part of the proof? Di pa tayo tapos kasi kailangan pa nating ipakita na unique, right? Kasi sabi ko, merong linear transformation. Susunod kong kailangang ipakita ay merong unique na linear transformation. Now, the last step is quite easy, So, let's see what was done here. I don't know why I wrote this part over here. I think that's kind of obvious, but let's see if that will be needed. So maybe we can start with this part of the proof. So suppose meron pang isang M na nag-exist such that ang M of B ay equal kay F of B. Kasi ang sabi ng theorem, if you remember, maybe we can scroll up. Sabi niya may unique L. So napakita na natin na may L na nag-exist na homomorphism na ang L of B ay equal sa F of B. Alright? So yun yung dinefine ko sa 46.1, which we have proven to be a homomorphism indeed. Now, the next question is, unique ba yung homomorphism na yon? So what I'm doing in the proof is I'm assuming that there's another homomorphism M. Okay? May isa pang homomorphism from V to W such that ang M of B ay equal kay F of B. And my goal is to show that M ay equal kay L for all vectors V. Yun yung gusto kong ipakita. Alright? So let's see how was it carried out. So okay, nag-suppose ako ng isa pang M ng M of B ay equal kay F of B. So in that case, kukomputing ko yung M of V para sa isang arbitrary vector V. Gusto kong ipakita, so we want to show that M of V ay equal kay L of V for all V. Kasi pag equal silang dalawa sa lahat ng V, ibig sabihin yung M ay equal kay L lamang. So ibig sabihin, unique lamang si L. Kasi pag may M pa na nag-exist, dapat equal lang siya kay L. Okay? Now, so computing ko kung ano si M of V. Si M of V ay equal sa M of the basis expansion of V. And again, this is crucial kasi madedefine yung function value in terms of the basis expansion, right? But here, I will use the homomorphic property of M. Kasi si M, sabi natin na isang homomorphism, so napreserve niya yung addition. So the image under M of a sum is equal to the sum of the images under M. Alright? Ito yung homomorphism property. Pwede kong i-add muna yung mga vectors bago i-plug in kay M, o kaya i-plug in muna kay M bago kunin yung sum ng vectors. Doesn't matter, they are equal to each other. So that's the justification from this line papunta sa line na to. And then again, I'm going to use the homomorphic property of M. Parehas lamang yung pag-scalar multiplication muna bago ipasok kay M, or ipasok muna kay M yung vector bago gawin yung scalar multiplication. Doesn't matter because the two are equal anyway. And so that's the justification here until here. All right? Pero saan equal ang M of BI? Ang M of BI ay equal sa F of BI. Alright? Kasama yung sa assumption natin ng M of B ay equal sa F of B. So ang M of BI ay equal sa F of BI. But this guy, taken as a whole, if you look at equation 46.1, bakit 49 yung nakalagay? Normally, sinasabi ko kanina pa. Yeah, that should be 46.1, I guess. Yeah, 46.1. So sabi ng equation 46.1, ito ay equal lamang kay V. Okay, 46.1. Siguro dito siya dapat nakalagay. By 46.1. Alright? So definitely unique lamang si L. Kasi pag may M pa na nag-exist, ang L dapat ay equal kay L. So that proves na, yeah, pag meron ka isang function, kaya mo siyang gawan or gawing isang homomorphism. All right? Questions? Wala pa naman so far? Okay, so let's look at some examples about this. Example 39 deals with the polynomial evaluation map. Alright? Ang ginagawa ng polynomial evaluation map ay minamap niya ang vector space of all polynomials papunta sa vector space consisting of the scalars. Alright? So, in such a way na kapag meron akong polynomial na alpha I, x to the I going from 0 to n, ang function value lamang niya under the evaluation map EV. So, ibig sabihin, ang pinaplug-in ko lang kay EV ay yung polynomial itself. Yung polynomial ay nagiging summation lamang ng alpha I t sabay. Na yung mga c sabay ay fixed na from the beginning. Okay? Or you can do it the other way around, na kapag meron ka mga c sub yung c sabay ay equal sa power ng fixed polynomial. Okay? Kaya yung evaluation map ni P ay equal lamang sa function value ng polynomial for a constancy. Now, this is a linear transformation, yung evaluation. Pag nagpa-plug in ka ng isang constant sa isang polynomial, that's an example of a linear transformation. Kasi ang ginagawa natin ay, pwede mo siya ipakita na linear transformation via the definition of a linear transformation. But you can use proposition, what was that? What's the title of that theorem? You can use theorem 19 para ipakita na siya ay isang linear transformation. Kasi pwede mo ditong sabihin na, okay, ang basis, ang gagamitin kong basis para kay f bracket x. Remember si f bracket x, ito yung polynomials. Set of all polynomials with indeterminate x, right? Siguro lagay natin yung degree kaya niya. Hindi natin kailangan ng degree. So pipili ka ng basis para sa kanya. Piliin mong basis ay yung elementary basis. So gamitin natin si 1, si x squared, si x cubed, and so on. Yan yung gagawin nating basis. Alright? Tapos mag-fix ako ng scalar f. So ito yung ipa-plug in ko papunta dun sa polynomial. Right? So halimbawa gusto mo ma-compute si p of c, right? So ang gagawin ko ngayon, i-fix ko na si c. Alright? Now, ang gagawin ko ngayon ay ang little f of c ay equals little f of basis element. So, f of 1 gagawin kong 1. Ang f of x gagawin kong c. Ang f of x gagawin kong x squared. Ang f of x ay gagawin kong x cubed. Alright? So, yan yung function little f dun sa theorem 19. Now, pwede akong makagawa ng isang linear transformation para sa kahit na anong polynomial. So, L of p will be the summation. Wag muna summation. Kukunin ko muna yung kanyang basis expansion. Halimbawa si polynomial p ay equal sa summation ng alpha I x to the I going from 0 to n, right? So makita nyo si x to the I, sila yung mga basis elements. So you start with x to the 0, which is 1, x to the 1, which is x to the 2, which is x squared, and so on. So sabi ng theorem 19, o ang turo sa atin ng theorem 19, si L ay magiging linear transformation kung i-define ko to be equal to summation ng alpha I f of x to the I going from 0 to n. Papalitan ko lang dun sa basis expansion yung x to the I, yung basis element, by the function value of the basis element. Essentially, ito ay magiging summation lamang ng alpha 0 c to the 0 plus alpha 0 c to the 1 plus alpha 0 c squared. Sorry, bakit ko siya in-expand? Wala na yung summation kasi in-expand ko lang siya. and so on. Sorry, not alpha 0. Sorry, what's happening? Yeah. It should be alpha 0. This should be alpha 1, alpha 2, plus alpha 3 C cubed, and so on. Hanggang matapos siya. All right? Which is essentially what we know in elementary algebra as P of C. Nag-plug in ka lang ng constant na C kay P. Now, since this evaluation map was so constructed, then we can say that evaluation of polynomials is a linear transformation. All right. So that could be that could be your argument for showing that the evaluation map for any polynomial is a linear transformation. All right. Okay. Now, ang sinasabi ng remark 4 ay, ng theorem 19 ay sa bawat isang function little f, arbitrary function f, makakabuo ka ng linear transformation. The converse is also true. Kapag meron kang homomorphism o isang linear transformation, makakahanap ka ng isang arbitrary function f. And so there is a one-to-one correspondence between the set of all homomorphisms from V to W to the set of all functions from the basis to W. So magkasing dami lamang ang mga linear transformations mula kay V papunta kay W at saka yung set of all functions mula kay B mula sa isang basis papunta sa vector space W. Now, this might tell us na mukhang marami palang linear transformations. Kasi magkasing dami ang linear transformations mula kay V hanggang kay W at saka yung set of all functions mula sa basis papunta kay W. And intuitively, it seems that mukhang madaling makakuha ng linear transformation. Kasi mag-define ka lang ng function mula sa basis papunta kay W, then makakapagbigay na yun sa atin ng isang linear transformation mula kay V papunta kay W. Now, actually, sabi ni Golan, nung author ng ating book, hindi siya ganun ka-common. Parang napakabihira ng mga linear transformations in the set of all relative to the set of all functions, because meron tayong mahigpit, meron tayong rigid and restrictive property na hinihingi para maging linear transformation. Dapat na preserve niya yung vector addition saka yung vector saka yung scalar multiplication. Pero pag binilang natin, or I'll show you an example here na napakaliit na fraction lamang ng set of all functions, yung set of all linear transformations. So tingnan natin dito. Halimbawa, mag-consider tayo ng common field. So again, ang field na titingnan ko ay si Z3. So siya yung underlying field. Tapos gagawa ko ng vector space consisting of quadruples of elements ni Z3, right? So kukunin ko si F4. Si F4 ay mga 4 vectors lamang, A, B, C, D, na bawat isa, A, B, C, D, ay nanggagaling kay Z3. Okay? Pag binilang natin kung ilan ang laman ni V, which is F to the fourth, ilan yung makukuha natin? Well, we have 3 options for A. Pwede siyang 0, 1, or 2. So may tatlong options para sa kanya. Kay B may tatlong options din, 0, 1, or 2. Ganun din kay C, ganun ka din kay D. So there's a total of what? Fundamental counting principle. Sa bawat isa, meron tayong tatlong options. So 3 options here, 3 times 3 times 3 times 3. So there's a total of 81 vectors dun sa ating vector space V. Okay? Tapos, so 81 yung cardinality ni V. Tapos, ang dimension ni V ay 4. Kasi F4 siya, right? Alam natin, madaling maghanap ng isang elementary basis para kay F4. Kasi ang elementary basis niya ay si 1, 0, 0, 0, si 0, 1, 0, 0, si 0, 0, 1, 0, at si 0001. Yan yung elementary or canonical basis para kay V. Ilan ang laman? 1, 2, 3, 4. So ang dimension niya ay 4. So ito pa yung isang magandang example ng pinagkaiba ng dimension at saka ng cardinality. The dimension of our vector space is 4, but the cardinality of the vector space is 81. Okay? Now, tingnan natin ilan yung lahat ng functions mula kay V papunta kay V. So tingnan natin yung mga functions, mga functions mula kay V papunta kay V. Ilan silang lahat? Well, si V merong 81 elements. Then bawat isang 81 elements doon, meron siyang 81 possible images. Right? So pag yung unang element ni V, tawagin natin siyang V1, meron kang 81 options. Pwede mo siyang i-transform papunta kay V1 pa rin, pwede kay V2, pwede kay V3, kay V4, kay V5 hanggang kay V81. Si V2 ganun din, meron ka ring 81 options. So kasi pwede mo siyang i-pair kay V1, pwede mo siyang i-pair kay V2, kay V3 and so on. So 81 options. All the way down to V81. 81 yung elements ni V, no? So si V of 81, meron ka na namang 81 options kung sino yung function value niya. Pwedeng ang gawin mong function value ni V of 81 ay si V1, pwedeng si V2, pwedeng si V3, and so on. So meron kang 81 options. 81 elements na tig 81 ng options, so there's a total of 81 to the 81 possible functions from V to V. So ang dami ng mga posibleng functions mula kay V papunta kay V. In particular, 81 to the 81. That's a very huge number. Pero ilan doon sa mga 81 to the 81 linear transformations? Alright? Ilan sa kanila? Well, thanks to Theorem 19, yung number of linear transformation from V to V ay kasing dami lamang ng kasing dami lang siya ng set of all functions from a basis papunta kay V. Yun yung sinasabi ng Theorem 19. Magkasing dami lang yung functions from B to V at yung homomorphisms from V to V. Right? So ilan ba yung basis elements? 4 lang. B1, B2, B3, B4. Kasi nga ang dimension niya ay 4. Now, ilan yung options ko para sa ipe-pair ko kay B1? Well, pwede siya si V1, pwede siya si V2, pwede si V3, pwede si V4, pwede si V5, hanggang V of 81. So here, I will have 81 options. Kasi nga function from B na may 4 na laman, papunta sa V na may 81 na laman. So bawat isang basis element, meron siyang 81 options. So ganun din to. So ilan yung laman ni f of BV? So first element, 81 options, second element, 81 options, third element, 81 options, last and fourth element, 81 options. So there's a total of 81 to the fourth options. So 81 to the fourth, yung dami ng functions from B to V. Eh sabi ng Theorem 19, magkasing dami lang yon as the set of all linear transformations from V to V. So 81 to the fourth lamang out of the 81 to the 81 possible functions yung linear transformations. Pag kinuha mo ilang percent yon, napakaliit. 81 to the negative 77, or in percent, that's 81 to the negative 79. So that means napakaliit lamang na fraction. So ang probability, pagka bumunot ka ng isang random function from V to V, ang probability lamang na makukuha mo ay isang linear transformation ay 0.11 times 10 to the negative 146. Ganon ka rare yung mga linear transformations. But despite this rarity, most of the functions that govern natural phenomena ay mga linear transformations. The way how sound travels in space, the way how electromagnetic waves travel from one transmitter to one receiver. Basically how we get signal to our cellular phones, how one text message gets transmitted from one phone to another. That phenomenon actually is governed by a linear transformation. So that's the nice thing about nature, ano, napaka parang perfectly designed ng universe and the processes within it, na sa dami ng mga functions na makakapag-map sa paraan ng pagta-transmit ng messages, ano, nagiging linear transformation pa siya. And in the simple example of Z3, ang liit ng probability na linear transformation yung makukuha mo na function. And it turns out that nature picked linear transformations as the governing law for most of its phenomena, right? So kaya ganun kahalaga yung linear transformations. Although napakakaunti nila, pero they often pop up from one application to another. Okay, now let's see. Can I finish some more? Maybe you let me just see which one I would like to end with. Kasi 8:20 na, no? So let's see. Let's see. Which one should I cover? Hmm. Okay, maybe let's look at the examples here. I think it would be nice to finish here. But before those examples, let's look at proposition 20. So napaka-rare na mga linear transformations, pero kaya natin gumawa ng mga linear transformations. I-follow lang natin yung ginagawa sa theorem 19. Pero pag meron ka ng theorem 19, nakagawa ka na ng dalawang linear transformations, madali nang gumawa ng additional linear transformations. You just need to get the composition of those two linear transformations. And proposition 20 guarantees that what you will get after the composition is yet another linear transformation. So let's straighten up some notations here kasi depende sa convention na ginagamit nyo or dun sa book na ginagamit nyo, no? So ngayon, meron tayong homomorphisms o linear transformations L and M. Si L ay function na nagdadala sa mga vectors V papunta sa mga vectors KW. Tapos si M, siya ay isang homomorphism na nagdadala ng mga vectors kay W papunta kay Y. So yan yung functional notation ng L at saka si M. Yung M circle L, yung composition, the same composition that you learned in your basic algebra courses. Hindi ko lang sigurado kung ano yung ginamit nyo, pero si M circle L or M composition L, ang gagamitin natin sa klase, siya ay mula kay V papunta kay Y. Alright? So siya yung function na magmumula kay V papunta kay Y. Magsimula kay V, dadaan ka kay L, tapos yung image kay L, ipa-plugin ko kay M para makuha yung image kay Y. Right? Hindi ko alam kung tinawag nyo to na M circle L or L circle M. Gusto ko siyang tawaging M circle L para mas natural yung plugging in. So I mean, what you'll do is, pag meron kang M circle L, alright, ang domain niya ay na kay V, tama? So ang domain niya ay si V, so magpa-plugin ako dyan ng isang vector V. Para ma-compute to, gusto ko yung M circle L notation para natural kung alam nyo kung kanino kayo unang magpa-plug in. You do the plugging in from right to left. So it is equal to M of L of V. Ipapasok mo muna si V papunta kay L, which is valid because si V ay nanggagaling kay V, tapos si L, tinatransform niya yung mga vectors V papunta sa vector in W. Tawagin natin itong M of W. Alright? Where L of V is equal to W. Si W ay nagagaling kay W kasi codomain ni L si W. Tapos pwede ko bang i-plug in si little w papunta kay M? Yes, because the domain of M is capital W. So ito ay well-defined, equal to kay Y, which is an element of the vector Y, the vector space Y. Okay? So ganun natin siya isulat. Alright? So baka nung high school kayo or nung college kayo, magkaiba yung sa composition, pero in the module, ito yung ginagamit ko. Alright? Ang claim ko ngayon, yung composition, yung dalawang linear transformations ay linear transformation pa rin. Okay? Now let's see how that is done. Okay? But essentially, ang mangyayari lang naman ay gusto kong ipakita yung dalawang bagay. Remember, dun sa definition natin ng linear transformation, gusto lamang nating ipakita na na-preserve yung addition saka yung scalar multiplication. That is exactly what I'll do, and I'll capitalize on the fact that both L and M are linear transformations. So, kunin ko yung M circle L, ipa-plugin ko sa M circle L yung V1 plus V2. Gusto kong ipakita na equal yon sa M circle L of V1 plus M circle L of V2. But again, you will see in the proof na pinaglaruan ko lamang yung definition ng linear transformation, pagiging linear transformation ni L at saka ni V. Ni L at saka ni M. Okay? Let's see in details what was done. Okay, start muna ako dito. Yan yung gusto kong i-manipulate para mapakita yung kabilang side naman nung equation, what was that? Nung definition 7.1 yata, if I'm not mistaken. All right? So, definition ng composition, M circle L of V1 plus V2, ipa-plugin ko muna yung V1 plus V2 papunta kay L. That's how we got that. Then the answer will be plugged into M. Pero, alam ko na si L ay linear transformation. So, pinipreserve niya yung addition ni V1 at ni V2. So, that means, yung L of V1 plus V2 ay equal sa L of V1 plus L of V2. Right? Kasi nga si L ay linear transformation. Tapos, gagamitin ko naman yung pagiging linear transformation ni L. Si L ay nag-a-act sa L of V ni M. Siya ay nag-a-act sa L of V1 at saka sa plus L of V2. Linear transformation siya. So, pwede ko munang i-plug in si L of V1 papunta kay M and get this guy. Tapos, i-plug in si L of V2 papunta kay M to get this guy and then sum them up according to the addition in the vector space Y. Alright? Pero ano to? Ito yung definition ng M circle L V1. And ano to? Ito yung definition ng M circle L V2. Essentially, napakita natin ng M circle L ng V1 plus V2 ay M circle L ng V1 plus M circle L ng V2, which is half of the work to be done. Right? The other half is showing that scalar multiplication is preserved. So kunin natin yung M circle L ng alpha V1, and the dream is to show that that is equal to alpha M circle L of V1. But similar to what was done earlier, I will just appeal to L and M being linear transformations themselves, right? Definition ng composition ay ito. Plug-in mo muna yung alpha V1 kay L, tas yung sagot ipa-plug-in mo kay M. That's what we got here, all right? And then si L kasi ay linear transformation. So that means the alpha can come out of L. Hence, we get this line. M madaya. Si M linear transformation din. So yung alpha na to, pwedeng lumabas ng M. And hence, we get this. But what is this guy? This is essentially the definition of composition. So that is exactly M circle L of V1. Remember, there's an alpha outside. So we have shown that scalar multiplication was preserved. And hence, M circle L is a homomorphism. Okay? That good? Any questions? Okay, mukhang wala naman. Hopefully may katulad na ganyan sa homework. Hindi ko natanda kung ano yung binigay ko sa homework for ano. Pero let's see what's next. It's defining inverses. Okay, maybe I'll finish the examples about inverses, and then probably on Wednesday we'll talk about kernels and ranges leading towards the rank nullity theorem. Okay, all right. Now, define natin yung inverse image ng isang element ng codomain. Now, in these discussions, we are considering an L, a linear transformation L, which takes a vector in V papunta sa vector in W. Right? So, siya si L. Now, pag kumuha ka ng isang element ni capital W, tawagin natin siyang little w. Right? I-define natin yung inverse image. So, this is read as the inverse image of W to be the set of all vectors in V such that L of V is equal to W. Right? So pag kinuha mo ang L inverse ni W, essentially what we are getting is a set. Ano yung set na ano yung set ng mga elements ng function value ay si W. So, collectin mo lang yung mga vectors dun sa domain na pag pinlogin mo kay L, ang sagot ay si W. Yun yung inverse image ni L. Image inverse ni W under L. Okay. Note that pwedeng walang laman yung L inverse W. You will see in the examples later na posibleng wala siyang laman. Kapag wala kang element ng domain na kayang i-plug in kay L para makuha si W, then the inverse image of W will be empty. Posibleng wala siyang laman. Ibig sabihin lang, walang element ang domain na nakakarating kay W or nagiging W after the linear transformation. Right? And then this term is very important, the kernel. Yung kernel ng isang linear transformation, and we denote it by ker-L, right? So yung kernel ni L ay lahat ng elements ni V nung domain na pag pinlog in mo kay L, ang sagot ay zero vector. So essentially, the kernel of L is the set L inverse of zero. Ibig sabihin, sino yung mga vectors kay V na ang image under L ay equal kay zero vector. Now, the thing is, the kernel is not empty. It will never be empty. Bakit never siya magiging empty? Or pwede ba siya maging empty? Pero sinabi ko na hindi siya pwede maging empty. Bakit hindi pwede maging empty yung kernel ni L? So, pag sinabi kong hindi siya pwedeng maging empty, so sure ako na lagi siyang may laman. Ano kaya yung laman niya? Na alam natin na lagi niyang laman. Kahit ano pa si L.
Yung zero of V po?
Yes, that's great, Sol. Ano? So kasi naalala ni Sol yung remark 3 kanina. Sabi natin, pag pinlagin mo yung zero vector kay V sa L, sa linear transformation L, ang sagot lagi ay yung zero vector in W. Now, ang kernel, hinahanap natin sino yung napupunta sa zero vector after function evaluation. Sabi pala, yung zero vector kay V, ang image ay laging zero vector in W. So, ibig sabihin, laging may laman yung kernel ni L. Ang laman ng kernel ni L, at least, ay yung zero vector dun sa domain. Right? So, kaya alam natin siya ay laging may laman. Okay? So, that's why it is always non-empty. Tapos dun sa inverse image, pwedeng set yung ilagay nyo sa kanya. So kapag meron kang set of vectors say U, sinulat mo yung inverse image ni U, hinahanap mo lamang sino yung mga vectors V na yung function value ay nandun sa set U. Okay? Makikita natin yan later, pero try to prove probably in the compre. I might ask you to prove that if U is a subspace of W, then the inverse image of U is a subspace of V. Tama nga ba? I think, sinama ko ba ito sa compre this year? This is a nice compre problem, so try to prove it. Yeah. So some specific examples before we end tonight's session. Example 41, para lang ma-illustrate ano yung konsepto ng inverse image and then the kernel. And then we'll reserve the we'll reserve the range for Wednesday, So yeah. Ngayon magko-consider ako ng isang specific example. So si L ay magiging isang homomorphism from F3 papunta kay F4. So triples with filled elements, quadruples with filled elements. So paano ko siya imamap? So yung mga na kay F3 gagawin kong F4. Paano? Ito yung root. Ito yung L na gagamitin natin. So pag meron kang vector V1, V2, V3 na nanggagaling kay F3, right? So ang gagawin kong image niya under L ay equal kay V1 minus V2, 0, V3, V3. Okay? Now, you can check that this is a linear transformation. So, kindly check that. Pakita nyo lang na napreserve yung scalar multiplication saka vector addition. I think that would be pretty straightforward. But just to drive the point of illustrating the previous definitions that we mentioned, uh, paano natin papakita, or let's see if we can agree that the inverse image of the vector 1, 1, 1 ay equal sa empty set. Ibig sabihin lang nito na kahit ano pang vector v1, v2, v3, yung i-plug in ko kay L, never ako makakakuha ng sagot na 1, 1, 1, 1. Why can I say that? Why are we sure about that? Na ito ay empty. Wala akong v1, v2, v3 na mapaplug in kay L para makuha si 1, 1, 1, 1. Why am I sure about that? Yes, Sol?
Kasi 0 po dapat lagi yung second, nasa
Yeah. 0 dapat yung second element palagi. So, ibig sabihin, pagka meron akong 4 vector nanggagaling kay F4 na non-zero yung second component, ang inverse image na ay laging empty. Kasi hindi tayo makakita ng V1, V2, V3 na pag pinlagin ko kay L equal kay 1, 1, 1, 1. Kasi pag sinolve niyo yung equation, dapat ang V1 minus V2 ay equal kay 1. That could happen. V3 equals 1, that could happen. V3 equals 1, that could happen. But 0 equals 1 is never true. Kasi in a field, ang additive identity ay hindi equal palagi sa multiplicative identity. Hindi equal palagi. Palaging hindi equal. Yun yung tamang term. Palagi siyang hindi equal sa zero, palaging hindi equal ang multiplicative at ang additive identity sa isang field. So that's why we can say that for sure this is empty. All right? Pero tingnan naman natin kung anong inverse image. Let's look for the inverse image ng 1, 0, 0, 0. How do we find the inverse image of 1, 0, 0, 0? Well, madali lang. Hanapin lang natin lahat ng posibleng V1, V2, V3 na pag pinlogin ko kay L, maging equal kay 1, 0, 0, 0, 0. So we're looking for the inverse image talaga. Kaya ganun yung pangalan niya, inverse image. Well, according sa definition, yung L of V1, V2, V3 ay equal kay V1 minus V2, 0, V3, V3. Equate ko lang siya dun sa gusto kong mahanapan ng inverse image. All right? And then look at the resulting equation. Well, this equation will require us to set V1 minus V2 equal to 1. 0 equals 0, that's fine. So, okay, hindi empty because that's an identity. V3 is equal to 0, V3 is equal to 0. So we get the system of two equations in three unknowns. So magiging totoo itong equation na to kapag ka si V1 minus V2 ay equal kay 1 at saka si V3 ay equal kay 0. Right? So that means ang itsura ng inverse image set ni 1, 0, 0, 0 ay V1, V2, 0. Right? Kasi nga ang V3 dapat fixed to be 0. Pero ang condition natin dapat si V1 minus V2 ay equal kay 1. Right? So examples ng mga vectors na nandito sa L1, sa L inverse ni 1, 0, 0, 0 ay halimbawa si 1. Si 1, 0, 0. Sino pa? Si, halimbawa, ang F natin ay R, halimbawa. So, meron akong say 2. Ano dapat yung second component? Dapat ito ay 1, 0. So, 2, 1, 0 is another element of the inverse image because if we plug in 2, 1, 0 into L, we use this formula, we're going to get 1, 0, 0, 0, 0. All right? Or we can also have, say, negative 3. And then what? Negative 3, and then we can have 4, 0. Negative, no, this should be negative 4. Negative 3, negative 4, 0. When plugged in to L, will it give you 1, 0, 0, 0, 0? Tama. Kasi ang condition lang naman ng V1 minus V2 ay equal kay 1. So we get negative 3 minus -4, that will be equal to +1. So -3, -4, 0 is a member of the inverse image of 1, 0, 0, 0. Okay? Is this clear? Kaya na ba mag-compute ng inverse image? I hope it is. Okay? So lagi nyo lang kukunin yung equation tapos isolve siya. Now, if we want to get the kernel, hanapin natin yung kernel ng L. So essentially, para lang mahanap yung kernel ni L, equate ko lang yung L of V1, V2, V3 papunta dun sa zero vector kay codomain. Ang codomain natin, remember, ay si F4 kasi si L ay member ng homomorphism set from F3 to F4, right? So ang zero vector kay F4 ay si puro zero, 4 na zeros. Alright? Kasi equate ko lang siya kay L of V1, V2, V3. According to the rule, ang L of V1, V2, V3 ay V1 minus V2, 0, V3, V3. So isolve ko lang itong equation na to, this guy equal to this guy, alright? And then we see that ano yung conditions? Dapat si V1 minus V2 ay equal kay 0, si V3 ay equal kay 0, and that's it. That's the equation that is satisfied by and only by those elements of the kernel. So we need to solve this. V1 minus V2 equals 0 and V3 equals 0. So then if you simplify the first equation, you're going to get V1 equals V2. Tama? So that means ang itsura lamang ng ating kernel ay dapat equal yung the first two components, tapos equal kay 0 yung third component. Right? So meron tayong what? Yeah, that's the kernel of the transformation L. Okay? Sige, one last example. Let's look at example 42. Ito naman yung medyo kakaibang homomorphism. So mag-start tayo. Ang domain natin ay set of all 2x2 matrices. Alright? Tapos imamap ko siya sa set of all polynomials of degree at most 2. So, degree at most 2. Yeah, that's fine. Alright? Kahit puro linear lang naman yung kakalabasan. So, ang ginagawa ng L, kumukuha siya ng isang matrix, tapos ang binabalik niya ay isang polynomial of degree at most 2. And how is it done? Via this rule. Kapag meron kang matrix na ang laman ay A, B, C, D, matatransform siya ni L sa isang linear function, isang linear polynomial. Ang linear function na yon ay equal kay A plus D plus quantity B plus C times X. Ganon nag-work yung rule. Okay? Now, it is your exercise to show that indeed L is a homomorphism. Gusto ko lang makita kung ano yung kernel. Again, para makita yung kernel, equate mo lang ito dun sa zero vector dun sa codomain. Ang codomain natin ay set of all polynomials. Alam natin kapag meron kang set of all functions, ang additive identity o yung ang zero vector natin doon ay yung zero polynomial. The zero polynomial is the polynomial 0 plus 0 times x plus 0 times x squared. Right? Tapos palitan mo lang to nung definition ng according to how L was given. Right? According to the definition of L, ito ay equal lamang. Ito yung L of ABCD. Ganun siya dinefine. Equate mo lang siya dun sa zero vector. But again, since we are equating polynomials here, the coefficients of the polynomials should be equal to each other. So we will write 0 as 0 plus 0x and match coefficients. Dapat yung constants ay equal dun sa constant na 0. Tapos yung coefficient ni x dapat equal sa coefficient ni x dun sa right-hand side. So essentially what we get is a plus d equals 0 and b plus c equal to 0. And then it's easy. You can solve this equation. You get, pero infinitely many solutions to kasi meron ka lang dalawang equations, pero 4 yung unknowns, A, B, C, and D. So ang relationship na makukuha natin dapat si D ay equal kay negative A pag kinompute mo yan. Tapos dito si B ay equal kay, si C ay equal kay negative B. Kaya naman, remember, ang itsura ng matrix na solution natin ay A, B, C, D. But we learned that, okay, A can be retained here, B can be retained here, but the C, the element in the second row, first column, C, is equal to negative B. So I can just replace that by negative B. And then the element in the second row, second column, D, can be replaced by negative A, according to this rule. This gives us um, a nicer and a more explicit form for the kernel. So, ang sinasabi ng computations natin dito, ang kernel ni L, yung mga vectors na pag pinlogin kay L, ang sagot ay zero vector, ay yung mga matrices ng itsura ay A, B, negative A, where A and B are arbitrary real numbers. Okay? Any questions with computing the kernels? This is very important kasi ang laki ng nilalaro ng kernel, ang laking role na nilalaro ng kernel sa mga linear transformations. And this will pay off because if you really understand the concept of a kernel, magagamit nyo rin yan sa abstract algebra. Kasi parehas lang din naman yung kernel ng group ring homomorphisms o field homomorphisms sa kernels dito sa atin. All right? Now, there's a hanging question here. Is the kernel a subspace of, is this kernel a subspace of R? Well, you can use the compact criterion, but there would be an easy way to do it. We just appeal to proposition 21. Sinasabi ng proposition 21, kapag ka meron kang linear transformation, yung kernel ng linear transformation na yon ay laging subspace ni V. But I think that will be too much if we will continue tonight. So that will be the starting point for the discussion on Wednesday. All right. So I think I'll end here. Any questions, guys? Pansin ko ngayon, super kakaunti ng umattend, 5 na lang. I don't know if there's a special event tonight or talagang nasa tail end na kasi ng SEM, so everyone is getting busier and busier. But again, that's fine. The silver lining of the online setup, we get to record meetings, so you can watch the recording or they can watch the recording later. But yeah, any questions habang nandito tayo? Burning concerns? Okay, so if there are none, then let's call it a night. I thank you for coming, guys. I hope you enjoy the rest of the evening, the rest of the weekend. Although I know mahirap i-enjoy itong mga natitirang panahon, 2 linggo ng semestre, but try the best that you can. For those who are still working on earlier homeworks, please pace yourselves because the uh, the the deadliest deadline that I can give you is probably the first week of April. All right. Sorry, not April. Bakit April? First week of August, because I think the end of classes is July 29. And then ang weird. I don't know if that's usual usual in OU. Ng end of classes yun na rin yung final examinations. Tama ba? July 29 din. Ah, so, but the grades are due August 12. So, I probably can give you another week. Pero sana wag tumambak. Kasi ang problema ko ay baka ako naman yung hindi makapagpasa ng grade by August 12. Probably I can give you until August 5 to submit everything. So that gives me 1 week to check all the backlogs. But if you can, please submit it by July 29. But if really hindi nyo kaya, then siguro by August 5, pwede pa. Mahabol ko siya. Kasi otherwise, i-incomplete ko na lang yung mga may kulang pa. Alright? Para hindi naman ma-delay yung grades ng mga nakapagpasa on time. Right? So that would be our deal. I'll elaborate on that next meeting. Until then, guys, keep safe and have a good night. Bye.
Thank you,
Bye,
sir.
Thank you,
sir.
sir.
Thank
Good
you
night
po.
po. God bless po.
Thank you, sir.
All right.
Thank you,
Welcome and
classmates. Good
salamat
night
po.
po. Bye.